We have Velcro strips attached to two carts. The cart on the left has a mass m and a speed 3 v0, and that's going to the right. The cart on the right has a mass 2m and a speed v0 to the left. The carts collide and they stick to each other very quickly. So we're going to draw a picture, find the velocity of the carts. We're going to organize our solutions here to make the graphing easier. So we have the cart on the left, and this cart has a Velcro strip right here, and this cart is mass m. And then we have a cart on the left, also with a Velcro strip, maybe it has like a mass on top. So this is 2m. Okay. What direction is the left cart going? To the right, with a speed of 3 v0. And the blue cart is going to the left, and v0 is its original speed. Okay, then they collide together and do what? They stick. So then my final picture, mass m, sticking to this cart, mass 2m, has a mass on it. All right, so let's write what we know. The mass of cart 1 is m. Its initial velocity is 3 v0. Cart 2, the mass is 2m, and its initial velocity is negative v0. Good, negative v0. And then for the two-cart system, what is the total mass? M plus 2m, which is 3m. Okay, and yeah, two-cart system, 3m. All right, so we'll talk about this in a second. So let's come over here. Anytime I draw pictures, what do I do for each picture? Write the equation for each. And what is the particular equation we're using here? M times v, right? Mass times velocity, because we're setting up our conservation of momentum. So anytime I have an explosion or anytime I have a collision, right, I'm setting up a momentum before equals momentum after, and I'm drawing the pictures before. So here's my before. So I have mass times 3 v0. So mass times velocity plus mass times velocity equals mass times, and in this case, the velocity is a final velocity. Okay, so I wrote a momentum equation for all of them. So let's take a look back here. What is the initial velocity of the red cart, or initial momentum of the red cart? What is it? Mm-hmm, 3m v0. So this is my initial momentum for the red cart. What's the initial momentum for the blue cart? Negative 2m v0. Now, here's the thing. We have 3m v0. Oh, I should just put minus 2m v0. What is this equal to? M v0. So when I'm talking about the two-cart system, right, that total momentum before is going to be m v0. So that's going to be the, oh, do you like how I put that in the wrong spot, you guys? Good thing I have a chart here. Total momentum before is m v0. M v0, that's the total momentum. Everybody okay so far? With momentum, mass times velocity, right? In the two-cart system, I'm looking at the momentum before equals the momentum after, and if that's the momentum after, what's the momentum after have to be? It will be 3mv final over here, okay? What I'm going to do over here, however, is I'm going to go ahead and make this MV naught. Why can I do that? Because it's the same thing. We're going to end up drawing graphs of everything, and we're going to have them in terms of V naught. So I'm going to purposely put this as V naught, but this holds true. Now, with that said, right, I want to take a look at the final velocities, right? Well, how could I solve for the final velocity here? So I'm going to divide both sides by 3m. So I get V final equals what? So 1/3 V naught. V naught over 3. Okay, now I'm saying that the final velocity is 1/3 V naught, right? Well, let's take a look. Over here, if these are sticking together, then what has to be the final velocity of the red? We just found the final velocity, right? Because this is the velocity of the two-cart system, right? So it all has to be 1/3 V naught for this last part. So this final velocity is 1/3 V naught. The final velocity of the blue, well, blue is stuck to red, so the final velocity of the blue is also 1/3 V naught. And for the two-cart system, okay, the velocity for the system is not changing. So this is going to be, for the system, 1/3 V naught and 1/3 V naught. Okay. Now this can be a little bit confusing. They're using the center of mass of the system to get that 1/3 V naught. We're going to talk about that more when we get to the rotational unit. Okay. But for the two-cart system, because we are not changing our momentum, right, and the total mass of the system is not changing, the velocity is not changing, okay, of the system. So the last thing we need to find is the final momentum. So final momentum for the red cart. Well, momentum is what times what? Mass times velocity. So my mass for the red is m. What is my final velocity for red? 1/3 V naught. So this is going to be 1/3 mv naught. So this is the momentum of the red. And then the momentum of the blue cart, what's the mass? 2m. What's the final velocity? 1/3. So the final momentum of the blue cart, 2/3 mv naught. All right, and now what we're going to do is we're going to graph these. So for the red cart, okay, so this is my red cart. And then this is going to be the symbols I use for the blue cart. And then we have our two-cart system. It's going to be purple. Okay. On the graph, I have labeled this T subscript C. That's going to be the time where the collision occurs. Okay, so it's just randomly placed on the graph. Okay, so we're going to plot momentum as a function of time for each cart and the two-cart system. Okay, so what's going to happen then is for the red, my cart on the left with mass m, my initial velocity, I'm looking at momentum first. My initial momentum is 3 mv naught, and I have that until the time of the collision. All right, now the carts collide and stick to each other very quickly. Okay, so very quickly would be essentially straight down. But then my final momentum is 1/3 mv naught, so that's going to be down here. So this is 1/3 mv naught. All right, so this was the red cart. The blue cart, what was the initial momentum of the blue cart? -2 mv naught. So that's going to, these are going to be circles. And that's until the time of collision. Once the collision occurs, my momentum changes to what? So I'm going to bring this up very quickly. And this is up to 2/3 mv naught. 2/3 mv naught. And now let's take a look at the two-cart system. So the two-cart system, because this collision was quickly done, we know that the conservation of momentum is conserved. So mv naught is initial, mv naught is the final momentum. So that's going to be like this. And this equals mv naught. Okay, so let's take a look here. Before the collision, what was the sum of the momentum of the carts? The sum of the momentum. So the total momentum of the carts before was mv naught. Take a look now. That momentum changed, but what's the sum of the momentum of the carts? mv naught. Now, the momentum did not change in the same way. Take a look. Which one had a greater change in momentum? Yeah, the red one had a greater change. Why do you think that that might be? Right? It was going faster and it weighed less. This weighed more, right? So some of that change in momentum, like the red one, is going to change more likely because it weighs less too. Now this one's hard because we have two differences. The speeds are different and the velocities are different. It's much easier to compare the two when we have one thing being the same. But let's take a hold off on this graph and let's take a look at their velocities because that'll make a little bit more sense. So for the velocities, we have our red cart starts at what velocity? So we have 3v naught, and then what did the final velocity change to? So we have 3v naught. And then it changes to 1/3 v naught. And what did the blue start at? What was the velocity of the blue initially? Negative v naught. And then that changed to 1/3. All right, so here we can see the change in velocity. And which one had a greater change in velocity? The red one. You can see, or I should say speed even. It had a greater change in speed, right? It was going really fast, and then it had a huge change in speed, and that's most likely due to the fact that the mass of this other cart was bigger in comparison. So it's harder to change that speed or change the motion of something with more mass. So that kind of goes back to our inertia laws too, okay? So an object in motion wants to stay in motion, the object at rest wants to stay at rest unless you have some sort of unbalanced force, but this is more massive, so it has more inertia, so it makes it harder to change the velocity in comparison to the velocity of the red cart.